everyone. This side Dr. Amit Kumar Pandey. I am going to discuss resource allocation graph and banker's algorithm in this lecture. So let's start. Resource allocation graph. So the resource allocation graph is a graphical representation used to illustrate the allocation of resources and process in a system. Nodes represent either process or resources. Edge represent resource request and resource allocation. RAGs or resource allocation graph are commonly used in deadlock detection and prevention algorithms. Nodes, process node or resource node. Process node represent a process in the system. Resource node represent a resource type in the system. There are two types of edges, request edge and assignment edge. Request edge indicate that a process is requesting to a resource, and assignment edge indicate that a resource is assigned to a process. We can see here, in resource allocation graph, there is a node. We represent with a circle. This is used for denoting a process. And for a resource, we use a node with a rectangle or a square. Just like this will represent a resource. And if we talk about edges, request edge, suppose there is a P1 which is requesting for R1. Then we can show it like that. Means a edge from P1 to R1. What it denote? It denote that P1 is requesting for R1. And if we take in another resource R2, and here is an edge from R2 to P1, this shows that R2 is already occupied by P1 or R2 in position of P1. Means this is an assignment link or assignment edge, or this is an requesting edge. Okay. Here is a diagram. You can see. Here is R1, which is already allocated to P1, and P1 is requesting for R2, which is already in position of P2, and P2 is requesting for R1, and R1 is already occupied by P1. So here you can see this is circular weight. Depiction using resource allocation graph. Now, when deadlock occurs when a cycle is present in the RAG. As we see in previous slide, there is a circular weight. That is a deadlock. For example, process A is waiting for a resource held by a process B, which is waiting for a resource held by process C, and so on until process N is waiting for a resource held by the process first A. The deadlock prevention strategies aims to avoid such type of cycles in resource allocation graph. Now, let's see Banker's algorithm. What is Banker's algorithm? Banker's algorithm is used in deadlock avoidance, or we can say Banker's algorithm is a deadlock avoidance technique used to ensure that resource allocation request will not lead to unsafe state. It was developed by Dijkstra, W. Dijkstra, The algorithm is based on the idea of a banker managing the allocation of cash to customers in a bank, ensuring that loans can always be paid back. So operating principle क्या है इसका? What is operating principle? The algorithm operates in a loop, continually checking if a resource request can be granted without leading to an unsafe state. It keeps track of available resources, maximum resources, and need of processes and currently allocated resources. A resource request is granted only if it does not result in an unsafe state. Means there should not be any chance for occurring a deadlock. Here are some terms which we will use in banker's algorithm. So available. This is a vector indicating the number of available resources of each type inside a system. Allocation. This matrix represents the number of resources each type allocated to each process. So how many number of resources and how type of resources are allocated to the processes. Max matrix represents the maximum demand or maximum resource need of any process. Need matrix represents the remaining resource need of each process after some allocation. Suppose process A want 10 resource of A type and we allocated 2 resource, then remaining is 8. So 8 is the need of process. Safety algorithm. A state is safe if there exists a sequence of resource allocation that satisfy all process need. What is the process need? Resource. They all want resource without leading to a deadlock. Unsafe state, a state is unsafe if it cannot guarantee deadlock avoidance. There are two subparts in banker's algorithm. First is safety algorithm or another one is resource request algorithm. So what is request? A process requests additional resources. Check the algorithm checks if granting the request will lead to be an unsafe state, grant or deny. Resource grant हो रहा है, deny हो रहा है. If the request can be granted without leading to an unsafe state, then it is approved. Otherwise, it is denied. Resource allocation. If granted, resources are allocated to the process. Otherwise, it waits. So this is the workflow for banker's algorithm. Now here we can see resource request algorithm. It is used for determining whether request can be safely granted. Let request be the request vector of process P. If request J equals to K, then process P want K instances of resource type of Rj. Request J equals to K. For process P. It means the process P want K instances of resource type J. Okay. Now, so what is the algorithm? If request of any process is less than equals to need, then continue. If request of any process is equals to less than need, then continue. Continue means step 2. If request is less than equals to availability in the system, then again we proceed. We will allocate the resource. After allocating the resource, the available will be available minus request. मीन्स अभी जो रिक्वेस्ट आपने फुलफिल की है वो आपने सिस्टम से जो रिसोर्स है उनमें से उठाकर आपने प्रोसेस को दी, तो जो अवेलेबिलिटी है वो आपकी कम हो जाएगी. कितनी कम हो जाएगी? जितना आपने उस प्रोसेस की रिक्वेस्ट में ग्रांट किया उसको, है ना. एंड एलोकेशन ऑफ पर्टिकुलर प्रोसेस, एलोकेशन आई, एलोकेशन ऑफ पर्टिकुलर प्रोसेस विल बी एलोकेशन प्रीवियस प्लस करेंट एलोकेशन करंट एलोकेशन क्या था, जो भी रिक्वेस्ट किया था वही हमने एलोकेट किया था, है ना. नीड ऑफ दैट पीआई, it will also decrease. Need will be previous need minus current allocation request. So these are the update after granting the resources for any process, not to any process. If request of particular process is not less than or equals to need, then raise an error condition since the process has exceeded its maximum. Okay. Suppose request is less than equals to need and request of I is not less than equals to current availability, then that process must wait since the resource are not available. If both okay, request is also equals to less than need and request is also less than equals to available, then we allocate the resource and will make these changes in the system. We will update available, we will update allocation of particular process, and we will update need of particular process. What is safety algorithm? We can check here. It is used for finding out whether or not a system is in a safe state. So find an index I for any process such that finish I equals to false. Means वो process अभी complete नहीं हुई है, terminate नहीं हुई है, ठीक है ना. If need of I is less than equals to work, what is work? Work is what is work? Work is currently available. So if process is not finished and the need of that process is less than equals to availability, ठीक है ना, then work will be work plus allocation. कब होगा, इसको हम प्रोसेस को एग्जीक्यूट करेंगे, एग्जीक्यूट करने के बाद ये टर्मिनेट होगी, तो टर्मिनेट होने के बाद ये अपना जो भी एलोकेशन है वो रिटर्न करेगी. जब रिटर्न करेगी then availability will be availability plus allocation of that process pi. In second step, if no such I exists, then go to step 4. What is step 4? Means all the process finish I equals to true for all I, then the system is in a safe state. All the process are checked and the system is in a safe state. Advantage and limitations of Banker's algorithm. Advantage that it guarantees deadlock avoidance. It ensures that resources are allocated in a safe manner, and limitations of Banker's algorithms are as it requires prior knowledge of maximum resource needs so that it may lead to a underutilization of resources due to conservative allocation. Numerical. For better understanding, here is a numerical. We will solve it. What is the numerical? An operating system uses the Banker's algorithm for deadlock avoidance when managing the allocation of these resources type X, Y, and Z to three processes P0, P1, and P2. The table given below presents the current system state. Here the allocation matrix shows the current number of resources of each type allocated to each process, and the max matrix shows maximum number of resources of each type required by each process during its execution. There are 3 units of type X, 2 units of type Y, and 2 units of type Z still available after allocating the resources to all these processes P0, P1, P2. The system is currently in a safe state. Consider the following independent requests for additional resource in the current state. Request 1, P0 requests 0 unit of X, 0 unit of Y, and 2 unit of Z, and P1 requests 2, 0, 0. So which of the following is true? Only request 1 can be permitted, only request 2, both can be permitted, or neither, or nor can be permitted. So availability is 3, 2, and 2. Okay. Right here, available X, Y, Z, 3, 2, 2. 3, 2. What are the requests? P0 require 0, 0, 2. It requires 0, 0, and P1 require 2, 0, 0, 2, 0. So current allocation is this: X, Y, Z. System allocated one Z type of resource to P naught, and 3 X type of resource and 2 Y type of resource to P1, and 2 X type of resource, 1 Y type of resource, and 1 Z type of resource to P2. Here we can see these are the maximum demand for each process for their execution. Now, if or after allocating all these, means if we talk about resource X, so there are 5 units which are allocated for Y, 2 plus 1, 3 units are allocated to all process, 4 Z, this is 2. This is the current allocation. After allocating these instances of every resource, we still have 3 resource of X type, 2 resource of Y type, and 2 resource of Z type. Now the request, if we talk about request 1 of P naught 002, so we have to check if 002, okay, first we have to calculate need. Need X, Y, Z. So what will be the need for P naught? 8 minus 0, 8, Y, 4 minus 0, 4, Z, 3 minus 1 equals to 4 P1, 6 minus 3, 3, 2 minus 2, 0, and 0 minus 0, 0. 4 P2, 3 minus 2, 1, 3 minus 1, 2, and 3 minus 1, 2. And this is the current need of every process. Now we check for a request of P naught 4002. So we have to check that 002 for P naught is less than need or not. Okay, 002 is less than need. Now we again check that request of P naught is less than equals to availability of system, then 002. Now okay. Now we will allocate P naught 002 X, Y, or Z, Z type, 2 instance of Z resource type to process P naught. So if we allocate, then Z will be 3. Allocation increase हो जाएगा. Z will be 3. And need will be 8, 4, and this will be 0. This will be 0. Availability will decrease. So now availability will 3, 2, 0. In the case of P. In the case of P naught, 320. Now we will check whether with current allocation and current availability, all the process will get executed completely. So let's check. If we will find any safe sequence, then we will grant P naught 002 resources without any hesitation because system will in a safe state. If system will not stand in a safe state, then request cannot be permitted. So check for safe state. Starting from P naught, the need is 840. Can the need of P naught can be satisfied with this availability 320? Not. Next, P1 300. This need can be satisfied with 320. So suppose the first process which will execute is P1, and after executing P1, P1 will release all the allocated resources. So these are 320, 320. Now total will be 640. Now check for next process P2. The need of P2 is 122. Can we satisfy this 122? As we can see, here are six instance of resource type X, 4 instance of resource type Y. That will be okay. Here demand is 1 and 2. But P2 need 2 instances of Z type also. We lack in this. So we cannot execute P2. Okay. Now check for P naught. The need of P naught is 840. This cannot be satisfied with this availability. So we cannot find, we did not find any safe sequence. So the request for P naught 002, this cannot be permitted. Now check for request P1 200. If we will check P00, so P1 200. So we can see 200. Okay, in next slide we can do it in next slide. It is a request of P1 is 200. Request of P1 is 200. X, Y. Here again we have to calculate need. X, Y, Z. Need will be 8 minus 0, 8, 4 minus 0, 4, 3 minus 1, 2, 6 minus 3, 3, 2 minus 2, 0, 0 minus 0, 0, 3 minus 2, 1, 3 minus 1, 2, and 3 minus 1, 2. Okay. What is availability? We can check from previous slide. Availability was 322. So check for this request P1 200. So is 200 is less than need. So where is need of P1? 300. That's okay, less than need. Now again check if the request is less than or equals to availability. So 200, okay, this is also fine. So we will allocate these resources to P1 and after that we will check for a safe sequence. So if we allocate 200 for P1, then this will be 520. When we increase the allocation, then need will decrease. So need will be 1, 6 minus 5.100. Okay. And availability will also decrease. Now availability will 1, 2, 2. Now check for the safe sequence. Can process P naught with need 842 will execute with this availability 122. We cannot satisfy the need of P naught with this availability 122. So P naught will not execute. Now check for P1. The need of P1 is 100, which can be satisfied with this availability. So we will execute P1 first. After execution, okay, again, there is some technical issue. Here is a need, name, X, Y, Z. 8 minus 0, 8, 4 minus 0, 4, 3 minus 1, 2. Now 6 minus 3, 3, 2 minus 2, 0, 0 minus 0, 0, 3 minus 2, 1, 3 minus 1, 2, 3 minus 1, 2, and availability was, we can check from previous slide, this was 322. This was 3, 2, 2, X, Y, Z. And what is the request of P1? We can check from previous slide. Okay, this is here. So we will resume it. Now check for P1. P1 can execute 100. The need of P1 is 100. So it can be executed with this availability 122. After execution, P1 will release all its allocation. So B provide 100, then it will return 100 again. So it becomes 122. And additional allocation, previous allocation, which was 520. So now availability will 5 plus 1, 6, 2 plus 2, 4, and 2. Now check for P2. The need of P2 is 122. So we can satisfy the need of P2 with 642. Yes, we can. So we will allowed 122 to P2 for its execution, and after execution, P2 will release all its allocation. So it became again 6 plus 2, 8, 4 plus 1, 5, and 2 plus 1, 553. 853. So P1, then P2. Now check for P0. Now, can we satisfy the need of P0 with this availability? Okay, 88543 2. Now, okay, we can satisfy the request, we can satisfy the need of P0. So it will also execute. And after executing, it will release all its allocation, which is 001. So this become 8, 5. As we can see in previous, that if we try for P0, then system we cannot find any safe sequence. When we cannot find any safe sequence for P0, then we will not allow P0. And while we calculate about P1, then it will give us a safe sequence which is P1, P2, P0. So we can say that we can allow P1 process. P0, P1. So there is option request to means P1 with request 2 unit of X, 0 unit of Y, 0 unit of Z. So only request 2 can be permitted. Okay. Now, summarize the lecture. Resource allocation graph and bankers algorithms are fundamental concepts in deadlock prevention and avoidance. RAG help visualize resource allocation and identify potential deadlock situations. Bankers algorithm provide a systematic approach to resource allocation, ensuring deadlock avoidance in the system. Together, they play a crucial role in ensuring the reliability and stability of operating system. Here are some references which I have used in my lecture. Thank you all. Thank you for being with me in this lecture.